I'm Jim Brunner. I'm a software development engineer at Amazon. I've been working on Redis and Valkey since 2019. As Jason would say, I'm working on the things that make Valkey boring. I'm responsible for incremental eviction, the monotonic clock. In Valkey 8.1, I redesigned active defrag to reduce latencies. And at Amazon, I've been working on boring features also, and forkless save is one of those. And now we're bringing that forkless save to open source. And that's what I'll be talking about today. So we'll start by talking about the save problem. And I know there's probably more than a few people here who have no idea what fork is. And this talk is for you. So hopefully it'll all make sense. We'll talk about what forkless is and what fork is, and then compare how these technologies differ, and talk a little bit about the roadmap going forward. So in version 1 of Redis back in 2010, there were two commands. There was a save command, two commands related to snapshot and save. There was a save command, and what that did is basically stop all the processing on the system and take everything that was in memory and copy it to disk. There's also the bgsave command, which essentially does the same thing, but uses something called fork to do that asynchronously. There have been no significant changes in this technology in the last 16 years, until now. So in Valkey 10, we're introducing an option to do save without using fork. And we'll talk about why that matters. So first, let's talk about what save is. So save, importantly, represents a single point in time. It's a consistent single point in time snapshot of the system. And the problem with Valkey is that this is an in-memory system that's running at super high speeds. So how do we save an in-memory database while it's running without impacting performance? That's the challenge. And up until now, we've used fork technology. Let's talk about that. So fork is an operating system function that splits a process into two identical processes. And we have the original Valkey process, which continues serving traffic and running normally. And then we have this forked process, which just sits around doing the save. In a forkless approach, we do the same thing with one process. We have a new thread in that process, which performs the save. But if you're not a tech geek, at this point, you're probably wondering why that matters and if you care. And you probably should care, and we'll talk about it now. So fork. Fork is really brilliant. It's been around in Linux forever. What fork does is with a single line of code, it takes a snapshot of a process. It's like a photograph of the process exactly as it existed at a moment in time. And it only takes one line of code and just an instant of time to do that, and we capture everything. And the way our bgsave works is after we've done this fork, then we can take our time and do the save, and we're just saving from that snapshot. So if fork is so brilliant, why do we need a forkless solution? Well, let's understand how fork works. So in Linux, the memory is divided into memory pages, and typically a memory page is 4K in size. And when you have a running process, every single memory address gets looked up through a page table. And what that does is takes a logical memory address in the process and converts it to a physical memory address of an actual page of RAM. When we do a fork, we split that process into two, and what happens is the operating system splits the page table, and both processes are now looking at identical memory. The problem with this is that we can't allow either process to modify that memory or it messes up the other process. So we have to mark all the pages as read-only. And so now we have two processes that are looking at a great big chunk of read-only memory. The bgsave process doesn't really care too much. The bgsave process is really just reading the memory and copying it to disk. So whether it doesn't really need to modify anything. But the active Valkey process, it's really important. The active Valkey process is constantly changing data. So what happens? Well, when a process goes and tries to update a read-only page, the operating system interrupts and it stops the process and says, hey, you can't do that. And what the operating system does for us is it takes that 4K page of read-only memory and it clones it. It creates a duplicate page. And we call that duplicate page copy on write memory. And so the operating system pauses Valkey for an instant, clones the page. Now we have two 4K pages. And then it updates the page table for Valkey, and Valkey can then continue. The problem is very quickly we can run out of memory. And think about your keys and values in Valkey. Most people use rather small keys and values. So you can actually save quite a few on a 4K page. You don't have to even touch all of your keys and values in order to have to clone all your memory. You just have to touch randomly a smattering of keys and values, and all of a sudden you're cloning all these pages. And that can double your memory use on the system. So let's talk about the specific pain points in fork. So first off, there's a startup cost. When you do that fork, there is a pause while the operating system clones the page table and marks all the pages as read-only. And I've measured that pause often at over 100 milliseconds, which is a pretty long time in Valkey. I've had other people tell me with certain configurations, large memory, lots of pages, that it can be over a full second. And stopping Valkey for a full second is a problem for almost any customer. Second, and the thing most people notice, is the memory explosion. We can get double the memory of our Valkey process while this is happening because we just clone all these pages. And lastly, most people don't recognize this, but there's a performance hit while we're cloning those pages. Each time we have to clone a page, there's an interrupt. It stops Valkey for an instant, clones the page, and lets it continue. And that's measurable. If you're running a performance benchmark, you can see that. Okay, so forkless save. When you just can't afford 50% of your memory sitting around being unused, just waiting for a save, we need a mechanism to do this without using fork. And so ThreadSafe is the name of our forkless mechanism that we introduced at Amazon. We've been using it at Amazon now since Redis 6 is when we introduced it internally. ThreadSafe performs the exact same save with no significant memory growth and no startup latency and some limited impact on the main thread performance. You're probably saying, well, that sounds great, but I know there's a catch, and you're right, there's a catch. Some clients that are doing writes are going to experience additional latency. So let's talk about how ThreadSafe works. So in the Valkey main thread, we're going to grab a small group of key values and we lock them. We prevent them from getting written to. We're going to send them off to another thread internally. And then that other thread is going to do all the heavy lifting. So we're not going to introduce a lot of work on the main thread, which bogs down your process. The background thread is going to do the serialization of the data and the saving to disk, the I/O. When the background thread's done with that, returns it back to the main thread, the values get unlocked, and everything can continue normally. But remember back with our snapshots, it's point in time. And we have to save everything before it can get modified. We have to maintain that point in time from the instant the snapshot was requested. And that means that if a client needs to modify a key value in memory, we have to save that key value first before we allow it to get modified. Okay, so that client has to wait. And we all know waiting is bad. Okay, so ThreadSafe has several optimizations that are going to mitigate that waiting. And the first one is that read operations are free. Read operations never have to wait. Even when the key is being saved, we can still read it. Second, with that is creates are free. If we're creating new data, the new data didn't exist at the point in time we're doing the snapshot. So even though it's a write, if it's new data, it doesn't have to be saved, and we can do that immediately. That's never has to wait. The ones that wait are the ones that are modifying the existing data, and we have to make sure that data gets saved first. And what we can do to mitigate the wait is we can expedite any of those keys to the front of the line. So if a client comes along and says, I want to modify key X, we can take key X and move it right to the front of the line, save that immediately so that we don't have to wait too long. And the third thing is that for small key values, we can clone them. And so if you're modifying a small key value, instead of making you wait, we'll clone the item, send the clone off to be saved, and allow that write to continue immediately. So let's compare how fork and forkless, what happens when we compare these two together. So we know about initial latency. With fork, we've got that high initial latency, 100 milliseconds or more. With ThreadSafe, it's negligible. Memory usage, on fork, we could go up to 2 times memory usage. That's a huge problem for most customers. ThreadSafe, no significant memory growth. Client latencies, we've got a very small copy on write client latency in the fork case. Usually that's negligible. Most customers don't notice it. In the ThreadSafe case, we can have high latencies on modifications for the unsaved key values. Save speed, if we use fork as our baseline for save speed, that's what we've got today. ThreadSafe's a little slower. In general, it's about 15% slower, maybe 20. There are cases where it's actually faster, so it varies quite a bit depending on the type of data you have. But save speed is not usually the concern for most customers. Point in time save, if it takes 10 minutes or takes 12 minutes, we don't care. So the biggest concern with fork is usually that memory. Although some customers are really concerned about that initial latency and they don't care too much about the memory. ThreadSafe, the biggest concern is latency for modifications of existing values. And this is especially noticeable if you've got very large keys. So if you've got a single large gigabyte or 10 gigabyte hash table in your database, it might be a reason not to use a forkless save. Okay, so what's coming up down the road? Save is just one part of the puzzle. There's really 3 pieces in this roadmap. The first piece is the forkless save and snapshot, which I'm talking about now. And that's being released in Valkey 10. The next part is full sync. I'm going to talk a little bit about full sync here because it's super interesting, and the last talk talked about it as well. And then finally is slot migration. And we use fork in full sync and slot migration as well, so we got to address that. So full sync is exciting because the consistency requirements are different. In a snapshot, we have to be consistent from the moment of the snapshot. But in a full sync, we have to achieve consistency by the end of the sync. At the end of the sync, the primary and the replica have to be in sync, but we don't have this single point where we have to be consistent at the beginning. So in a save operation, all the keys have to be saved before modification. In a full sync, we have this interesting choice where we can send a key to the replica first and then send replication. Or we can modify the key on the primary first and then send the modified key. And this eliminates the need for blocking of clients in most cases. And if we look at it visualize this, we can think about processing our keys from one side to the other. We've got keys that are processed, we've got some that are in progress, and some that are not processed. You can see that we have to block the modifications and save for everything that's not been processed yet. But in sync, we only have to block modifications for that small set of keys that we're currently processing. Okay, we also have a very unique opportunity in the way full sync operates. So full sync today with a fork operates like this. First, we do a consistent snapshot. We use BG Save the same way we do a snapshot. We send that snapshot to the replica. The replica then loads that snapshot. And meanwhile, while all of this is happening, we store up every single modification that's occurring in the system. We store it in a giant buffer, and then we have to play back that buffer on the replica. ThreadSafe can do the same thing, But we can do something quite a bit different. We're incrementally sending the keys and values. And what we can do is selectively incorporate the replication that's tied to those keys and values into the replication stream. So there's no buffering at all. And the replica can apply that replication immediately as it occurs, again, with no buffering. So ThreadSafe gives us the opportunity to completely eliminate that replication buffering. And it reduces our network costs because we cut our transmitted replication by about 50%. Slot migration has very similar concerns to full sync replication. We do use fork today. It's not as big of a deal because we're only forking or only saving a portion of the database, so the fork time is much shorter. But with forkless capability, we'll be able to do the exact same thing with slot migration that we're doing for full sync, and that's what's coming up down the road. And I think that's my 20 minutes. Thank you. If you have any questions, I'll be around.